Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So as you know that within this module we are trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module we are currently on the fifth topic, that is time sharing. So within this topic, we will be talking about how what is time sharing and how it is implemented via this concept of CPU scheduling. So in the previous few videos, we have already talked about what is time sharing, what are the different aspects of time sharing, and what was its origin. So in short, it is basically a way in which since there are limited number of CPUs in the computer system and the number of processes that have to be run on these limited number of CPUs is way more than the number of CPUs. So we have to share the CPU between all of the processes. And the way we do that is that we frequently switch the control of the CPUs between the processes. And this is called time sharing. We are sharing the CPU time, right? So this was about time sharing. And we talked about that time sharing is essentially a resource allocation problem, right? We have to allocate the CPU as a resource to the multiple entities, that is the resource processes that want to execute on the CPU. So we have to do CPU scheduling, that is decide that which process should next execute on the CPU. So now we are going to formally talk about the different aspects of CPU scheduling. And the first thing that we will talk about is how does the CPU scheduling happen, right? So in this and the next two videos, in basically we'll spend three videos understanding the overall mechanism that makes CPU scheduling even possible. So what are the different mechanisms that make the CPU scheduling possible, right? So without further ado, let's get started. So let us start the discussion about CPU scheduling, right? So in the previous video, we defined what is CPU scheduling. So it is essentially a resource allocation technique, right? Simple. There is a resource that is the CPU, and there are several entities that want to use this resource, that is the processes. These processes have to execute on the CPU, and the number of entities is more than the number of resource. So this resource is in scarcity, right? We have limited number of resources, so we have to do a careful resource allocation, right? Very simple. So this is the concept of CPU scheduling, that is we have to decide that at which time which process will run on the CPU, right? So we have to basically allocate the CPU time to different processes so that all of the processes get a fair chance to execute on the CPU, get their instructions executed, and make progress. So this is the overall idea behind CPU scheduling. So we raised several questions, that is, if you are about to design a CPU scheduling mechanism, right? If you're an OS developer or something and you have to design a CPU scheduling technique, so what are the different questions that you must answer, right? So these are the different questions, as you can see: why, how, when, who, and which. We already know why we are doing scheduling, so that we can run more number of processes on limited number of CPUs. So in this video and the subsequent two videos, we are going to talk about the how part, right? So the how part is basically concerned with, first of all, how to do the CPU scheduling, right? Only when we have designed a mechanism that makes CPU scheduling possible on a system, then we can talk about other questions like when to do it, who will do it, which process to select when doing CPU scheduling. Those are secondary questions if you compare to the how question. The how question is much more important. First of all, you need to define, you need to design a mechanism where we can even do CPU scheduling on a system, right? So let's start with this how question. So for that, let's look at this time sharing diagram, right? So as you can see, we have a hypothetical system and we have three different processes. We have seen this diagram in the previous videos also, and we have only one single CPU, right? So we have one CPU and three processes, and what the operating system is doing, it is doing CPU scheduling, right? You can see this is the CPU time, and it has been allocated to different processes, right? So for some time process P1 gets to run, then for some time process P2 gets to run, then we switch the control to process P3, and in this way we allow all of the processes to execute on the CPU. So you can see that the CPU time is literally shared between different processes. So all of the processes get to execute for some time on the CPU. So this is one example of CPU scheduling. Now we are going to talk about how to do this scheduling. So as we discussed, let's look at one of these switches, right? When the process is running, then we don't have to do anything. The real thing happens when there is a switch between two processes, right? This is where the CPU has to be scheduled by the operating system. So let us take a closer look at what all the things that we need to do and that we need to design to make a process switch possible, right? So we are going to focus on one of this switch. So you can see basically whenever there is a switch, before the switch there is some process running, that is process, let's say process A, right? And after, so then there is a context switch, right? Basically we are switching the processes, and this there is a term given to this switching between processes. That term, formal term, is called context switch, right? And after this context switch, we resume the execution of some other process. So initially process A is resuming executing, and after the switch, process B comes into the picture, right? And all the things that we talked about, all of the CPU scheduling will happen in between, right? So what is context switch? We'll talk about this in later videos in detail, but in short, it is basically switching from one process to another. So when you halt one process, you have to save the context, right? In which it was executing. Basically, as a process, when a process is executing, a whole bunch of things are happening in the system. As the process is executing on the CPU, the contents of the CPU registers are changing, the memory is changing, right? The uh, process might be interacting with some IO devices. So there's a whole bunch of things that is happening when the process is executing. And when you're halting that process, right? You're halting that process, you have to save all of the things that you're doing, so that at a later point in time, you can see this process will be resumed. In this example, this process is resumed at a later point in time, right? So the thing is that you're stopping the process before it is finished, right? You're halting the process even before it is finished. So it is obvious that it has to be resumed at a later point in time. And in order to do that properly, you have to save all of the you have to save the context, right? We call it context. You have to save enough information so that you can resume that process exactly where you have left it, right? So to resume the process exactly where you had left it, you have to save enough information, and that enough information is called as context. So that is what we are switching. And when we start some other process, we are bringing in the information like the context of another process. We'll talk about context switch in detail, right? So making the context switch possible is also part of the how question. So let's see what other things are part of the how question. So if you expand this context switch, you'll see what all the things are happening. First thing you have to do is that you have to transfer control to OS. Then you have to once the control is with the operating system, then the operating system can select some other process to run. This is just selection, right? We're not yet switched. It has operating system has just decided to basically, let's say, execute process B after process A. Then operating system actually makes the switch, right? And the control is then transferred to the um, next user process, right? So these are the things which have to be done at a high level, right? So in this video, we are going to talk about the first part, that is how do we transfer the control to the operating system. So the thing is that when process A is running, right, if you have to pay attention here, that process A is running, and the process A will not give up the control of the CPU on its own. It might, but there is no guarantee, right? So unless process A gives up the control of the CPU and transfers the control to operating system, until then we can't do anything, right? To do all of these things, that is selecting a different process to execute and making the switch happen, you have to halt the process, save the information, load another process. All of these things is the responsibility of the operating system. And not just responsibility, it's only the operating system that can do all of these things. It is even allowed to do all of these things, right? So the point is that all of these CPU scheduling that we are talking about, none of that can happen if the operating system is not running. And as you can see, when process A is running, then by definition, operating system is not running. And we can't do anything unless the OS is running. So what do we do now? The first thing is that we need some way to transfer the control to the operating system, because process A will not give up the control of the CPU on its own. I mean, it can, but there is no guarantee, right? So when you are writing your program, right, you do not include any kind of logic per se that you will be very kindly, very politely giving up the control of the CPU when your program is running. Nobody writes their program so that, I mean, whenever we are writing a program, we always write it with this mindset that we will have a dedicated CPU, right? We'll have the CPU for as long as our process is running. We never think about that when our process will be running, then it has to be stopped and some other process has to be resumed, right? So time sharing and this CPU scheduling is transparent to the programmer. The view of the programmer is that their program will be running from starting till end without interruption. Although we know that CPU scheduling happens, but we don't program it like that. it has to be done. This CPU scheduling has to be done forcefully. That is the point. And the operating system has to be brought into the picture forcefully, because uh, the process A will not, any process would not give up the control on its own. So this is a problem, right, that we need to solve, that how do we transfer the control to the operating system so that even we can start scheduling the CPU, right? So the first question that we need to answer while designing any CPU scheduling algorithm, any CPU scheduling mechanism per se, first thing that we have to design in this mechanism is that how do we first transfer control to the operating system so that anything subsequently that has to be done can actually be performed. So let's look at the different approaches that exist that allow us to transfer the control from the currently running process to the operating system. So let us discuss the different approaches that we have to solve the problem that we just described, right? The problem that we want to solve is that how do we transfer the control from the currently running process to the operating system, right? So what are there are two ways to solve this problem. One is called the cooperative approach, and the other is known as the non-cooperative approach, right? So let's discuss these two. First, we will talk about cooperative approach, and in the next video, we will discuss about non-cooperative approach, right? So what is this cooperative approach? Basically, here we are expecting the running process to cooperate with us, right? We are expecting that the running process will cooperate with the operating system and it will give up the control of the CPU on its own. So how does that happen? So basically, the operating system waits for any kind of traps to happen, right? So we already know what is a trap. We have discussed about traps in the previous one of the previous topics, right? So a trap is basically a event, basically which transfers control to the operating system, right? For example, we have system calls, exceptions, and interrupts. So let's see these events. We'll talk about these one by one. So these are events basically which transfer the control to the operating system on its own, because some kind of basically the some kind of routine has to be executed by the operating system to service these events, right? So this approach where we basically we are trusting the process to cooperate, right? We are expecting that the process will give up the control of the CPU on their own when one of the trap happens, right? This approach was used in early systems, that is Macintosh OS and old Xerox Alto system. These are examples of systems where this approach used to be followed, right? So let's now see what is this approach actually. So as I discussed, there are different kinds of traps, and whenever one of these traps happen, the control is transferred to the operating system. So the first example for a trap is the system call, right? So as you can see in this timeline diagram, we have a process, right? So there are two parts to this diagram. There is this user process. So all of these blue arrows depict that the user process is executing, and all of these red arrows mean that the operating system is executing. And here what we are doing is that we basically start a process, and when we are executing the process, very often we require the basically the process requires the services of the operating system, and that it can get via the system call. So we have talked about system calls. It is basically the user process requesting the operating system to perform some operation on its behalf. There are several operations which only the operating system is allowed to do, right? Because they are privileged in nature, most likely because they are involved with accessing the hardware directly. So it's only the operating system that is allowed to interface directly with the hardware, and all of the operations, right, that are related with the hardware, so they are encapsulated into the system calls. And whenever the user process needs one of these operations, it requests the operating system to to perform these operations via a system call. So whenever such a request will happen, you can see the control will go into the operating system. The operating system will then uh, execute that system call on behalf of the process, and somewhere in between, after let's say the system call is over, or even before that, the operating system can decide to make the switch. Once the operating system has the control, it can do anything, right? It has the control over the entire system. So the only part that we are interested here in is that we need control of the CPU, and that can happen if the user process makes a system call. Once the user process makes a system call, the control immediately goes to the operating system. System call is a type of trap, and whenever a trap happens, control is given to the operating system. right? And there are several system calls, and a user process often needs very frequently the during its lifetime, a user process very often needs system calls. There is very limited what a user process can do over the hardware. It often needs the operating system to do things on its behalf. So this is one of the way where we can get the control of the OS. Let's look at other ways also. So another case when we can get the control of the CPU is that when there is an exception in the system. An exception is a trap. And what is an exception? It is basically when the CPU discovers any kind of unexpected event or error, any kind of unexpected event or error during the execution of the process. And this typically happens when the application misbehaves, right? So it could be the case that there are bugs in the program, or it's a maliciously written program and it causes an exception. So there are several examples of exception. For example, if a user process tries to do something which is privileged in nature, for basically something which is a privileged operation and can be done only in the kernel mode. Basically, it's only allowed by the operating system, and the user process is trying to do such things. Let's say access a privileged memory location, or execute a privileged instruction. So these are uh, things which are illegal and they are not allowed. Whenever the CPU detects that the user process is trying to do something of this nature, then it raises an exception. And whenever there is an exception in the system, the control immediately transfers to the operating system so that the operating system can deal with such exceptions, right? With application misbehavior, whenever there is an application behavior, the operating system has to handle it, right? So that the operating system can deal with that misbehavior, maybe terminate the process or handle it in a more graceful way. Whatever is the reason, the control is given to the operating system. Other examples of other causes of exceptions include, let's say there is a segmentation fault. The process accessed unallocated memory, then it is a segmentation fault. It could be stack overflow, that is the limit of stack has been breached, or there could be a divide by zero error. One of the examples of what different errors can be caused. So all of these errors or unexpected events cause exceptions. Whenever the CPU detects such an exception, the control is immediately transferred to the operating system to take preventive action. So again, we can get the control if the process makes a error. And this can happen. We can reasonably expect that one of the processes will cause an exception, right? And the last example for different kinds of traps, the last example is that of interrupts. So what are interrupts? Interrupts are basically raised by devices, IO devices, and they are raised whenever any of the IO devices needs attention immediately from the operating system, right? It could be the case that any input operation or an output operation which had been previously started, that has finished and data is available, or the IO device is ready to accept more data, these kind of attention. Or it could be the case that there is some new input at some IO device like the keyboard or the mouse, and we have to immediately deal with that data, because if the user is typing something, then that has to be processed immediately. Or if the user is moving the mouse, that also has to be shown immediately in a responsive system. Or it could be something more important, or let's say dangerous, like the battery is going down, the battery is very low, or the temperature of the CPU is very high, CPU is heating up. So these kind of alerts could also be there. So in short, what I'm trying to say is that interrupts are basically situations when any kind of IO device needs attention from the operating system. And whenever there is an interrupt, the operating system, basically the interrupt is detected by the CPU. And what happens is that CPU stops executing the instructions of the current user process and immediately transfers control to the operating system, as you can see, to service that interrupt, right? So when the CPU is executing instructions, it detects after every instruction whether there is an interrupt from any IO device or not. And when it detects that there is an interrupt from any device, it will immediately transfer control to the operating system so that that device can be tended to. Whatever attention, whatever is the device trying to notify, the operating system needs to take immediately note of that and service that interrupt, right? So this is another example of a trap and a case where we can get the control of the CPU and give it to the operating system. So this was about the cooperative approach. In cooperative approach, we are basically trusting the user process, right? And assuming that it will behave reasonably. And uh, often, basically for one of these reasons that we discussed, it will give the control to the operating system. Either it could call a system call, right? It could invoke a system call, or there could be some kind of exception, or even some kind of device. Basically, whenever here, when there is a device interrupt, right? Here we do not require the cooperation of the user process. Mostly we require it in the case of system call and exception. But the point is that there are several ways in which we can implicitly get the control of the CPU and assign it to the operating system without doing anything special. So these are basically, you can just wait for any kind of trap to happen, right? So this was about the cooperative approach. And as you can see, we are putting too much trust on the operating on the user process. We are assuming that the user process will behave in a reasonable manner, which is a bad idea. Right now we'll discuss why this approach does not work, or even if it works, it's not safe, and why we do not use cooperative approach anymore. So this cooperative approach that we talked about, right, for transferring the control of the CPU to the operating system, it clearly has a issue. We are trusting the user process too much, right? So let's take an example where trusting on the user process can go bad, right? As you can see in this slide, let's say you start a process and it starts executing instructions, and we never have a trap, right? Let's say there is no device interrupt. The user process does not make any kind of system call or exception. So even if the chance of this might be low, but let's say that it does happen. So what do we do in this case, right? And this user process is buggy. It has a infinite loop. Just taking an example, there could be many other reasons why the user process is not terminating, right? Let's take a simple example that you started a user process and it has an infinite loop. So clearly it is not making any system call. It is not doing anything that will cause an exception. And let's say none of the devices need attention, right? Clearly we have a case where there's a process that has hogged up the CPU. So when I say hogged up, basically it has taken control of the CPU and it will not give it up. So unfortunately, if such a thing happens, what do you think you have? What options do you have? Unfortunately, you have only one option, that is to do it the hard way, that is reboot the system, right? Because the user process is not going to give up the control of the CPU. So, and you cannot stop that process, let's say, right? So in that case, you have to take a hard decision and you have to take the reboot, right? So when you reboot the system, when you reboot the system, uh, basically everything, obviously all the processes get killed, and the system starts in a fresh state. So this is how we will have to go if things go wrong, right? So this is the problem with trusting the user process, right? We are expecting the user process to behave in a reasonable manner in in this cooperative approach, right? And you could think, like, let's say you could say things like, okay, as a user I can press control C or do a cross button and try to terminate the program, right? But let's say there is no user, this process is running on a server, right? There is no end user sitting in front of the machine. The machine is just a server, and this process is started. So without intervention, the things basically you cannot fix these kind of issues. So clearly cooperative approach is not the way to go. And as I said, it was only used in earlier systems, right? Back in 60s 70s when we had Macintosh OS, right? One of the examples. So cooperative approach has its issues, that is, expecting the process to behave properly is not a good idea, right? We discussed this. So like the problem that we're trying to solve, right, that is getting the control to, like, transferring the control to the operating system, that is clearly not working out via this cooperative approach. Nonetheless, we discussed this because this used to be one of the ways to do things previously. So the other way, that is the non-cooperative approach, we will discuss this in the next video and see how we can actually transfer the control to the operating system in a more robust way, right? So this was about cooperative approach. And before I mean, like, end this video, I want to talk about a very useful thing, that is reboots are useful, right? You would have definitely seen this meme, right? So the point that I want to make, that when you are in a situation and your machine is not behaving properly, then rebooting is a good idea, right? And it is not just a hack that you might think that is a blind hack. No, it's not just a hack, it's a time tested approach, and there are reasons for it. So why does rebooting your computer solve many of your issues? So first thing is that when you're writing the operating system is a trusted piece of code. And when you reboot the system, we start from a state that is the fresh state of operating system. We start from a state which has been tested and which is known to work properly. So we are moving software back to a known and tested state. So when you reboot the system, whatever was the state of the system, that will be cleared out, and the system will start with the operating system booting up. And we know that the operating system is a safe and trusted piece of software. So when the operating system starts up, initially everything is correct, right? So that is why rebooting fixes many of your issues. Some other points about rebooting your system is that all the resources get reclaimed. There could be many cases that you have allocated some resources and they have been kind of lost. So you would have heard about this memory leak, right? So if you're allocating memory on the heap and you're not deallocating it, right, then there are memory leaks. There could be other kind of resource leaks. right? So all of those resources are reclaimed, right? So if your CPU usage was high, your memory usage was high, due to which your computer was working in a sluggish way, all of these things get solved. Due to lack of resources, whatever issues might be there, those will get solved. And finally, one important point is that these reboots happen in servers periodically, right? You as a user would often, you'll start your computer, and then definitely after using it some time you will close it, right? But in servers which are long running systems, where there is no one to manually start and close the system, they have scheduled reboots, that is, from time to time, periodically, after some amount of time, the server gets rebooted to bring the system back to a fresh state, to get it rid of errors, right? So the point that we discussed, in the case of the cooperative approach, if things go wrong, if the user process is not giving up the control of the CPU, we said that reboot is the options. And as a software engineering principle, right, while using the system, it is a good idea, if something is going wrong, then it's a good idea to reboot the system. Most likely it will go away. It is not guaranteed, obviously, but many times it often goes away. So I just wanted to talk about why it's not just a hack, it's a time tested approach. So guys, this was it for this video. In this video, we started discussion about how to implement CPU scheduling. We started with the how question, right? What are the things, what are the mechanisms that we need to have, so that we can even do a context switch, we can even do CPU scheduling. And the first question that we first problem that we raised is that how do we give control to the operating system? And then we talked about the cooperative approach of doing it. We clearly saw that there are issues with it, and in the next video we are going to see the alternative approach, that is the non-cooperative approach, that we call to transfer the control from the user process to the operating system. Once the control is with the operating system, then we can start doing the CPU scheduling. So guys, this was it for this video. Thank you very much for watching. I will see you in the next video.